Good morning, everyone. I, Aditya from BSC Chemistry Honors second year, is today here to explain the chapter of Chemistry of Actinides for the visually impaired students. Let's start with the introduction. Actinides constitute a series of elements following actinium in the seventh period of the periodic table. Actinides belong to the F block as these are formed by the gradual filling of 5F subshell. We have discussed the chemistry of lanthanide in the previous chapter. Lanthanide, which follows the lanthanum with atomic number 57, involve the gradual filling of the 4F subshell. In this chapter, we will discuss the chemistry of another series of 14 elements which follows actinum with atomic number 89. This series of 14 elements is known as actinides. Actinide along with lanthanide constitute the complete F block elements. The ending "ide" in the actinides is not appropriate because it is more correctly means negative ions such as oxide or chloride. Actinides were also named actanes by the group of scientists. However, the ending "on" is used preferably for the non-metals such as boron, silicon, etc. Whereas all the actinides are distinctly metallic. IUPAC has now recommended these elements to be actinoids with the ending "oid" rather than being actinides or actinons. However, it is unfortunate that people still call these elements by their earlier name as actinides. Before World War II, the only natural occurring elements actinides, namely thorium, proctanium, and uranium, were known. Uranium is the heaviest natural occurring element. It was after World War II that the remaining elements were artificially discovered through the nuclear reactions. These elements were man-made or synthetic elements. Another name coined for these elements is transuranic elements. Transuranic elements are the elements that have atomic number greater than 92. Let us now discuss the interesting aspects of the chemistry of actinides. Position of actinides in the periodic table. An inspection of the periodic table reveals the electronic configuration of noble gases radon as 6s2, 4f, 14, 5d10 and 6p6. After radon, the 7s and 7p orbitals gain stability relative to the 5f orbitals because s and p orbitals are penetrating than the d and f orbital. As a result, the next two electrons are being filled in the 7s orbital, which mark the appearance of new element francium and radium belonging to the s block elements. After the addition of two electrons in the radon core, the 5f and 6d orbitals penetrate the 7s orbital. The least penetrating 5f orbitals are stabilized on the account of the increase in effective nuclear charge outside the next noble gas core with increasing atomic number. As a result, the next 14 elements from thorium to leucranium enter the 5 subshell. It is important to note that around actinium both the 5f and 6d subshell possess almost similar energies. Because of similar energies of 5f and 6d subshells, the incoming electron may either of the two subshells, which result in the uncertainties of the electronic configurations. As a result, it is doubtful whether the electron enters the 5 subshell or not. For example, the configuration of thorium may be written as 5f06d2 7s2, or it may be 5f16d1 7s2. However, once filling start in the 5 orbital, the 5 subshell become more and more stable. As a result, from uranium onward, the 5 subshell become more stable as shown in figure 1. Thus, all the incoming electrons start filling progressively in 5 orbitals. F orbitals, sorry. The general electronic configuration of actinides can be assigned radon 5f0 to 14 6d0 to 1 and 7s2. The general characteristics of actinides. Some of the general characteristics of actinides are detailed below. Electronic configuration. As already discussed in the section 5.1, the actinides involve the gradual filling of the 5f subshell. The electronic filling of the titled actinium is radon 6s61 7s2. Thus, from thorium onward, the 5f subshell start progressively filled. The general electronic configuration of the atoms of the actinides in the ground state may be written as radon 5f1 to 14 6d0 to 1 and 7s2. The detailed configuration of all the elements are present in the table 5.1. Physical properties. Some of the physical properties of the actinides are presented in the table 5.2, which are discussed below. Melting point and boiling points. The melting and boiling points of actinides are moderately high but are lower than those of transition elements. An inspection of table 5.2 reveals that there is no regular trend in the melting and boiling point of the unknown actinides. Density. An inspection of the table 5.2 reveals that the elements near uranium have very high densities. Americum resembles the correct corresponding lanthanide. Europium is being less than its neighbors. Ionic radii and actinide contraction. The size of actinide ion decreases regularly along the actinide series. This is because with increasing the atomic number, the extra charge on the nucleus is poorly screened by the f electrons. This steady decrease in ionic radii with increase in atomic number is called actinide contraction. A comparison of M3 plus ionic radii of actinides with those of lanthanides revealed that actinide and lanthanide ion are very similar in size. As a result, their chemical properties are also similar. The decrease in ionic radii of M3 plus and M4N ion in case of actinide is shown in table 5 figure 5.2. It is interesting to note that there is a decrease in atomic radii from thorium to uranium, which may be due to increase in the most stable oxidation state from +4 to +6. In other words, the metallic bonding from the thorium to uranium may be considered to consist Mn plus ion with a total of n electrons for atoms. After plutonium, the metallic radius increased significantly again, which may reflect the increasingly lanthanide-like behavior of the later actinides, in which the preferred oxidation state is +3 with only 3 electrons per atom available for the metallic bonding. Oxidation state. The actinide elements show the greater range of oxidation state than the lanthanides, particularly in the early part of series. The different oxidation state of the actinides elements are shown in table 5.3. The +2 oxidation state in case of actinides are very rare. Am +2 has the configuration of 5f7. It is the analog to the uranium 2 plus in the lanthanides but exists only in the solid state as the fluoride AmF2. On the other hand, Cf2 plus Es2 plus Fm2 plus Md2 plus and NO2 plus exist ions in the solution. The properties of divalent actinides resembles more closely to the barium 2 plus in the group 2. The most stable +2 oxidation state is exhibited by the nobelium as NO2 plus and correspond to the stable 5F14 arrangement. The +3 oxidation state is the most common oxidation state among all the actinides. However, this is not always the most stable oxidation state in the actinides. The first four elements, that is thorium, PaU and Np, do not show +3 oxidation state as the most stable oxidation state. For example, uranium 3 plus is readily oxidized in air as well as in solution. Interestingly, the most stable oxidation state of the elements up to uranium is one the involving all the valence electrons. Thus, the most stable oxidation state of thorium, barium and europium are +4, +5 and 6 respectively. Although neptunium shows oxidation state +7 by involving all its valence electron, and it is not the most stable oxidation state. This is because neopium is in +7 oxidation state is highly oxidizing and the most stable oxidation state is +5. The +4 oxidation state is exhibited by all the elements from thorium to Cf. However, Pa and Np display the most important +4 oxidation state. The M+4 ions are known in the acid solution and are PPT by the fluoride, phosphate and ioxate ions. The elements all form dioxides MO2 and fluorides MF4. The +5 oxidation state is exhibited by all the elements from barium to americum. However, plus 5 oxidation state is the most stable oxidation state for neopium and panium. It is important to note that the M plus 5 ions do not occur in the solution as such. In fact, these states occur their oxocations such as MO plus 2 ions. A few solid compounds are known, whereas in solutions, these ions disproportionate rapidly. The plus 6 oxidation state is exhibited by the lower actinides, that is uranium, neopium, plutonium and americium in their form of fluorides. The plus 6 oxidation state is more commonly found as dioxo ion, that is MO2 plus, and the ion MO2 plus is linear and exists both in the solid as well as in the solution. One of the most commonly encountered compounds of uranium in the plus 6 oxidation state is uranyl nitrate dihydrate. UO2 NO3 twice, that is 2H2O. It consists of the UO2 plus ion surrounded by two NO3 minus ions and water molecules as shown in the figure 5.3. The nitrate ions are bidentate and therefore two oxygen from each nitrate are bonded to uranium. Oxygen atoms from the two water molecules also bond to uranium. The oxidation number around is uranium is 8. The UO2 2 plus ion in unit in the compound is in the compound UO2 NO twice and H2O twice is perpendicular to the hexagon of 6 oxygen atoms, 4 from the bidentate nitro group and 2 from water molecules. The lower oxidation state are ionic while the higher oxidation state are increasingly covalent. The plus 7 oxidation state is known only in the oxocations of neopium and plutonium when alkaline solutions are oxidized by the O3. The important oxo anions in the case in neopium and plutonium are NPO4 OH twice 3 minus and PuO6 3 minus. Color of the ions. Actinide ions are mostly colored. The color of the particular actinide ions depend on the number of the electrons present in f orbital. The color of the actinide ion arises mainly due to the FF transition. The color of the characteristic cations formed by the actinide ion, that is M3 plus, M4 plus, MO2 plus, MO2 plus in aqueous solution are given in table 5.4. In addition of the FF transition in actinides, then color also be aroused due to FD transition as well as charge transfer transitions. The color of the actinide ion solution because of FF transition occur in the visible and UV regions. We have already encountered of this FF type transition in case of lanthanides as well. Since the F5F electrons in case of actinides are projected out more in space than 4F electrons in lanthanides, since these 5F electrons are strongly influenced by the ligand's field of the ligand. This makes the absorption spectra of the actinides more complex compared to the straightforward spectra of lanthanides. A complex spectra is always different to characterize easily. It has been experimentally found that the absorptions due to FF transition in case of actinides are nearly the 10 times stronger and 2 times broader than the FF transition of the lanthanide ions. The energy difference between the 5F and 6D orbitals in case of actinides being smaller than 4F and 5D orbitals in case of lanthanides, the actinide ions invariously absorb light of lower frequency. As a result, the allowed and very strong FD transition lie in the UV region and therefore do not influence the color of actinide ions. It has been observed that the actinide ions in higher oxidation state display predominantly charge transfer spectra. This spectra is exhibited only by the higher oxidation state ions, which can easily oxidize the ligands. It is important to note that the lanthanides do not exhibit the charge transfer spectra because lanthanides do not display oxidation state higher than 4. Magnetic properties. The actinide shows similar magnetic properties to the lanthanides in terms of magnetic moments with the number of unpaired electrons. This is shown clearly in the figure 5.4, where the magnetic moments in Bm are plotted against the number of unpaired electrons. It is important to note that high valence state have been chosen for 5F1, 5F2, 5F3 and 5F4 ions, which shows close similarities. Magnetic moment values for the isoelectronic actinides ion are lower than the lanthanide ion. Example, niobium in 6, cerium in 3rd, niobium in 5, and niobium in 4 and D3. This is due to the fact that 5f electrons in actinides are projected more in space to the crystal field. As a result, the partial quenching of the orbitals occur by crystal field effects. Reactivity. The actinides are highly reactive metals. These react with dihydrogen and form non-stoichiometric hydrides with the formula MH2 or MH3. They react with the hot water and tarnish in air, forming an oxide coating. The actinides react readily with HCl, but reactions with acid is more slower than expected. The metals are basic and do not react with the sodium hydroxide. The actinides react directly with the halogens to form a variety of halides. The redox potentials for the known M3 and M couples are about 1.9 volt. Occurrence and isolation of actinides. All the elements beyond actinium in the periodic table are radioactive. As a result, the nuclei of all the actinides are unstable and undergo radioactive decay. Among the actinides, uranium is the heaviest natural occurring element with an abundance of 2.4 ppm in the earth crust and is more abundant than mercury and silver. Among the actinides, thorium and uranium occur on the earth because of the isotopes that are have half-life sufficiently long in view that the fact the earth was found several million years ago. Uranium. Since uranium is the most important of all the actinides, its chemistry will be discussed in more detail. The primarily natural source of uranium is pitch blende or uranite, which has the empirical formula U3O8. It is a mixed oxide containing uranium both in 4 and 6 oxidation states such as UO2.2UO3. The other important ores are caronite, eutenite, and calcium caronite. Extraction of uranium. As already mentioned, the main source of uranium is pitch blende. The details of extraction of uranium involve the following steps. Concentration. The ore is crushed to a fine powder and is subjected to conventional gravity separation to remove the lighter impurities. Roasting. The concentrated ore is roasted on the hearth of reverberatory furnace in the presence of air to remove the volatile impurities such as sulfur, arsenic, and antimony. Acid treatment. The roasted ore once is treated with dilute H2SO4 in the presence of oxidizing agents such as MnO2 or NaClO3. This treatment converts uranium to a soluble uranyl sulfate UO2SO4. The roasted ore are converted to the solution of UO2NO3 twice by dissolving the ore in the nitric acid. Treatment with ammonium carbonate. Addition of ammonium carbonate to the above solution of urine sulfate PPT, it has ammonium uryl carbonate. Conversion into uranium dioxide. The mixed uranium dioxide U3O8 is reduced to UO2 by heating either with charcoal or with hydrogen. The production of ammonia. Elemental uranium can be produced from the uranium dioxide by using either of the two methods. UO2 is heated with vapors of HM to form the uranium 4 chloride, which in turn react with magnesium to yield the uranium metal, or by converting UO2 to a volatile uranium tetrachloride by heating it with the elemental chlorine in the presence of charcoal. This is followed by the reduction with the elemental sodium. All the steps discussed above, which can be summarized in the flowsheet diagram for the extraction of uranium. Chemistry of separation of neptunium, plutonium, americium from the uranium. The three elements neptunium, plutonium, and americium that follow uranium in the actinide series are produced mainly from uranium in the nuclear reactors. If you recall, uranium is the old known element among the actinides. The natural occurring uranium contains two main isotopes which occurs in the ratio of 99.3 and 0.7 respectively. This is the another isotope which occurs in traces only. Neptunium and plutonium were prepared for the first time in 1940 by a team of celebrated scientists by bombarding uranium with neutrons in the cyclotron in Berkeley, USA. Both the elements are now obtained from the spent uranium fuel elements of the nuclear reactors where they are found by the capture of neutrons produced in the fusion of uranium fuels. Isotopes of plutonium. Plutonium can also be prepared by the reaction in which a fast neutron is added with the subsequent loss of two neutrons without allowing time for the intermediate products to decay. Americium can be obtained from the isotopes of plutonium by the success of N, gamma reactions in the nuclear reactor as the yields of the heavier elements after americium are controlled by two factors: the half-life of various isotopes and by their ability to absorb the neutrons. It is important to note that the stepwise addition of the slow neutrons is very difficult. A quick method is to bombard the nucleus with a large number of fast neutrons without allowing time for intermediate product to decay. For example, it adds a fast neutron then loses two neutrons to form isotope of plutonium according to the reaction. The separation of neptunium, plutonium, and americium from are based on the following chemistry. Stability of the oxidation state. A steady decrease in the stability of IE oxidation state with the increase in atomic number have been observed with the increase in atomic number. The order of the stabilities of the major ions are Am3 plus is greater than Pu3 plus, that is greater than U4 plus, whereas in the order of the oxoanions it follows the order UO2 plus, NPO2 plus, PuO2 plus, and AmO2 plus. Separation of these elements from uranium, from fission products, and from another can thus be achieved by adjusting the solution containing them to a stable redox potential and then using solvent extraction or precipitation. For example, plutonium can be oxidized to PuO2 plus while Am remains Am3 plus. Thus, plutonium can be removed by the solvent extraction, whereas americium can be pipetted by AmF3. Extraction into organic solvents. The MO2 plus ions from the solution can be extracted into the organic solvents. The M4 plus ions are extracted into tributyl phosphate in the kerosene from the 6-NHNO3 solution, whereas M3 plus ions are extracted from the 10 to 16-MnHO3. Precipitation reactions. Actinides in +3 and +4 oxidation can also be pipetted as their fluorides or phosphate from the acid solutions. Ion exchange method. The ion exchange methods are commonly used in the separation for the small amount of materials, as in separation of americium. Spent uranium fuel rods removed from the nuclear reactors can be used to extract the plutonium and neopium in kilogram quantities, whereas americium in 100-gram quantities. This reprocessing of the nuclear fuel rods is an important technology as they help to extract new elements that may be used as nuclear fuel. Spent fuel rods are dipped in the ponds of water for several days to allow them to cool. During this dipping period, the intensely radioactive isotopes with short half-lives lost most of their activity. Transuranic elements. Elements with the atomic number greater than 92 are known as transuranic elements. Before the Second World War, the elements thorium, protactinium, and uranium were located below hafnium and tantalum and tungsten in the periodic table. The synthesis of neptunium, a new element with the atomic number 93, by MC Million and Epsilon was demonstrated by bombarding uranium with the neutrons. This newly discovered element should be positioned immediately to the right of tungsten below rhenium. However, the properties of neptunium resembled more with uranium rather than rhenium. It was the discovery of neptunium followed by the subsequent synthesis of new elements that were responsible for the new series of elements called actinide series. All the transuranic elements are radioactive in nature and have short half-life period. Neptunium, plutonium and americium were unknown prior to their synthetic preparation via nuclear reactions. However, these elements were later found to be present in trace quantities in uranium ores. Synthetic routes to the transuranic elements. There are two synthetic routes which are commonly used for the synthesis of transuranic elements. A neutron may be captured by the nucleus with the emission of gamma rays and gamma reaction. The neutron increases the mass number of the nucleus by 1 unit and some energy is released as gamma radiation. Further, neutrons may be added in a similar way. Addition of neutrons increase the neutron to proton ratio. This makes the nucleus unstable because it contains too many neutrons. As a result, the nuclei decay by converting a neutron into a proton, a alpha beta part and a beta particle that is an electron. This reduces the NP ratio and also increases the atomic number by 1. Thus, a new element is formed. The other method involves the capture of small ions by the heavy nucleus. This is possible only if the bombarding particles have sufficient energy to overcome the Coulombic repulsions between the ion and heavy nucleus. The smaller ions are accelerated in a linear accelerator or cyclotron to possess the sufficient kinetic energy. The simplest ion used is the alpha particle. This increases the atomic mass unit by the several units, the atomic number by 2 units. Synthesis of transuranic elements. All the transuranic elements have been prepared by the nuclear reaction which involve the bombardment with either in the neutrons, alpha particles or small nuclei. It was prepared by Macmillan and Epsilon at Berkeley, USA by bombarding the uranium with slow neutrons when uranium isotope was obtained. Preparation of plutonium. It was discovered by Seaborg and his co-workers due to the beta radiation of Neptunium. Plutonium was named after the planet Pluto. Preparation of americium. Americium was synthesized by bombarding the uranium with alpha particles. Curium. Curium was synthesized by bombarding the plutonium with the alpha particles. Berkelium. Berkelium was synthesized by the Seaborg and his co-workers by bombarding americium-241 with the high-speed alpha particles. Preparation of californium. Californium was synthesized by bombarding curium with alpha particles. Preparation of einsteinium. It was synthesized by the bombarding U-38 nucleus with accelerated nitrogen nuclei. Preparation of fermium. Fermium was synthesized by bombarding einsteinium with neutrons, and the preparation of mendelevium was synthesized by bombarding einsteinium with the alpha particles. Preparation of nobelium. Nobelium was synthesized by bombarding curium with the accelerated stripped carbon. Preparation of lawrencium. It was synthesized by bombarding the californium-250 with the accelerated boron nuclei. A synthesis of the transuranic elements along with the half-life is given in the table. The later or heavier actinide elements, the elements from curium onward, namely curium, berkelium, californium, einsteinium, fermium and mendelevium, nobelium and their lawrencium, named as later actinides. Very little is known about the chemistry of these later actinides because of their limited availability and extreme instability. The availability of some of the most accessible isotopes are given in the table 5.6. It is clear from the table that curium is available only in macroscopic quantities, whereas the later actinides above atomic number 100 have been prepared only in minute quantities. In other words, later actinides were available in very tracer amounts. It is interesting to note that the later actinide shows close resemblance to the lanthanides. However, the actinides can easily be separated from the lanthanides because the actinides readily form the complexes. For example, the actinides react with the concentrated HCl to form the corresponding chlorocomplexes. If both group of ions are absorbed on the cation exchange column, the actinides can be eluted more conveniently with the concentrated HCl. After eluting the actinides can be separated from each other by ion exchange using the citrate solutions to elute them. It is interesting to note that in order in which tripositive actinides ions are eluted shows a close similarity to the order in which tripositive lanthanide ions are eluted. Figure 5.7 displays the Eulertian diagram for the actinides and the lanthanide elements. The first identification of the element from Americum to Mendelevium on a wettable scale was made through the elution. All the actinides with atomic number 96 to 103, with the exception of nobelium, have plus 3 as most stable oxidation state. The most stable oxidation state of nobelium, this is due because of the most favorable F14 electronic configuration. Actinides with atomic number 98 to 102 has also displayed the plus 2 oxidation state, except from the nobelium. Plus 2 oxidation state is strongly reducing in the nature. Higher oxidation state of curium are found in the solid state in the compounds such as CmF4 and RbCmF5. Elements beyond the atomic number 103, the actinide series is complete at lawrencium. We have learned that the half-life of the later actinides beyond atomic number 100 decrease considerably. For example, the half-life of nobelium is only 3 seconds. It has been calculated that the half-life of the elements will decrease further as new elements are discovered. The half-life of an element with an atomic number 108 is to be expected very short, about 10 power minus 4 to 10 power minus 6 seconds due to spontaneous decay. As a result, it is extremely difficult to synthesize and study the chemistry of elements beyond 108. However, these difficulties have not damped the spirit of scientists, and then they have successful in discovering elements up to the atomic number 112. Out of 112 known elements, elements up to atomic number 109 have so far have been named. A major controversy came to light over naming these elements. The choice of the name of the element belonged to the discoveries or discoverers. In the case of post-cat actinoids, 3 nuclear facilities are in competition for the synthesis of each of the newly discovered elements. The facilities are at Berkeley, California, Dubna, Russia, and Darmstadt, Germany. It is extremely difficult to identify which nuclear facility had the true claim. For example, the discovery of the element 104 was claimed by both USA and Russia groups. The Americans named the element Rutherfordium after Ernest Rutherford, while the Russians named it Khrushchevotium after the Igor Khrushchev. While these conflicting claims were being settled, the IUPAC devised a hybrid Latin Greek numerical system of providing provisional names and symbols to all the newly discovered elements. The names are derived directly from the atomic number using roots for the 3 digits in the atomic number of the element and adding IEM. The roots for the number and their abbreviations are: for 0 it is N, for 1 it is U, for 2 it is B, for 3 it is T, for 4 it is Q, for 5 it is pent, for 6 it is hex, 7 for sept, 8 for oct, and 9 for M. In some cases, the name are shortened by removing the repetitive letter. Example, Bi plus Im can be written as Bm, tri plus Am is known as trium. Let us name an element with the atomic number 106 according to the hybrid Latin Greek nomenclature. The name of the element is derived by combining together the roots of the order of digits which make the atomic number IEM in the end. 106 is equal to UN1, NIL0, and HX6. It is known as unihexium. The symbol of the element unihexium with an atomic number in is UNH. Similarly, the name and symbol for the element with atomic number 102 can be worked out as unilibium, not unibarium. The IUPAC name for the compounds with more than atomic number 100 are given below. The new recommended names for the elements 104 to 109 are mentioned in the table. Comparison of actinides and lanthanides. Both the lanthanide and actinide constitute elements of F block as they involve gradual filling of 5f orbitals. These elements occupy a distinct safe space at the bottom of the periodic table. They show close resemblance in some of their properties but also differ in many properties. Let us review some of the important points of similarities and difference among the lanthanides and actinide. Point of similarities. Both the lanthanide and actinides involve filling of 5f orbitals. Both include predominantly the +3 oxidation state in the most of their compounds due to poor shielding effect of 4f and 5m electrons. Both lactalide and lanthanide shows gradual contraction in the size of their atoms with increase in atomic number known as lanthanide and actinide contraction respectively. Element of lanthanides and actinides with the same number of unpaired electrons display similar absorption spectra due to FF transitions. Both are highly electropositive and very reactive. Nitrates, sulfate and perchlorates of trivalent lanthanides and actinides are soluble in water. Hydroxide, fluoride and carbonates of trivalent lanthanides and actinides are insoluble in water. Both the lanthanide and actinides can be separated by ion exchange method. Point of differences. Metallic orbitals, it involves the filling of 5f orbitals, whereas actinide filling the 5 of the 4f orbitals. Energy gap between 4f and 5d orbitals in lanthanide is very large. In actinide it is so small. Binding energies of 4f orbitals are higher than in lanthanides, whereas the binding energy of 5f orbitals in actinides are lower than in actinides. Oxidation state, the most probable oxidation state is +3, whereas in addition to +2 and +4. Shielding effect, 4f electrons exert greater shielding effect than actinides. Ability to form oxocations, lanthanide do not form oxocations where actinides can form the oxocations. Color of the ions, most of the lanthanide ions are colorless, whereas the actinides ions are colored. Complexing ability, the tendency to form complexes is small, whereas the tendency to form the complexes is large. Radioactivity, all lanthanides except promethium are not radioactive, whereas in actinides all the actinides are radioactive. Coordination number, lanthanide display coordination number 6, 7, 8, 9 and actinide display higher coordination number 8, 9 and 12. Basic character, compounds of lanthanum are less basic in nature, whereas the compounds of actinides are more basic in character.